All right, so there's a little bit more we need to know about how different crystal structures interact with X-rays or vice versa to allow us to figure out what the crystal structure is by using this X-ray diffraction technique. And so with that, we need to know about what we call the extinction rules. All right, so let's look at a simple case here. So this is a cube repeated 3 times, right? So we just have 3 unit cells here. But let's look at the 0, 0, 1 family of planes, right? So basically the bottom plane and the top plane here. And then we have the Bragg angles, we have the diffraction experiment at that angle theta. So let's say we're at the angle at which we have diffraction. And so in this case, with this system, you see a simple cubic, right? We have only atoms on the corner, so there's nothing elsewhere. So this is just simple cubic or primitive cubic. And so we would expect diffraction to occur in this case, right? We have diffraction occur. However, well, what we want to do is we want to look at a different scenario now. So for simple cubic, we would observe this 0, 0, 1 family of planes. But now let's look at BCC. Let's compare the same type of structure, but add that body-centered atom here. So this atom, if we repeat it for the different unit cells, we see that the body-centered position, this plane is actually known as the 002 because it's halfway through. And so what happens is that it's the same plane, just kind of halfway between our 001 planes, right? So what happens is that the fact that we have atoms now in the middle here actually cancel out the constructive interference between the top plane and the bottom plane. So having that middle plane now cancels out and causes destructive interference. So the 001 planes destructively interfere with the 002 when you have that plane. So therefore, if we do the same experiment at the same angle, what we see is that the body-centered cubic structure doesn't have a diffraction peak for the 001 because it always gets canceled out by the 002. So the placement of the additional atom there causes destructive interference, and so that basically makes that 001 diffraction peak extinct. So that's why we call it extinction rules. So obviously, if you're thinking about a system, you can't kind of go through and just visually see that this is going to happen. And so these have all kind of been calculated, which planes will diffract and which ones will not. And they've been put together in extinctions or reflection rules. And so that's what's given here in the table. And this is also in your textbook as well. This is in Callister. So these missing peaks can be summarized. And so here we're just dealing with simple cubic, FCC, and BCC. So for simple cubic, there's none of these missing peaks. So the first, if we do a diffraction experiment, we would see the 100, the 110, 111, 200, 210, 211 in that order. Those are actually the first diffraction peaks that we'd see, right? So if we go back to a typical pattern, right, these would correspond to those peaks if that was the case. So first, second, third, etc. So along the axis we're talking about. All right, so let's go and look at some of the other ones now. So basically all of the reflections are present for simple. But when we have FCC now, and we have those face-centered, so on the face of each cube, we have those face-centering atoms. Now what happens is that you only have reflections if the plane, the Miller indice values of the plane, H, K, and L, are either all odd or all even. And so if that sounds a little confusing, let's look at some examples over here. So if we have the plane 111, H, K, and L are all 1, right? And 1 is odd. So all of them are odd. Here, 0 and 2, those are both considered even. 2, 2, 0, again, all of those indices are considered even. 3, 1, 1, all of those are considered even. 2, 2, 2, 4, 0, 0. So all of these are either all odd or all even. Any other plane doesn't occur. So if we kind of consider the 1, 0, 0, 1 is considered odd, 0 is considered even. And so that's mixed. And so we don't see it in FCC. Or if we look at 2, 1, 0, 2's even, 1's odd, so we don't see it, right? So that's the rules for FCC. And so the first 6 peaks that you would see would be in this order: 1, 1, 1, 2, 0, 0, 2, 2, 0, 3, 1, 1, 2, 2, 2, and 4, 0, 0. And then up to BCC. In this case, the rules are that the sum of the indices has to be even. So again, if we look at some examples, if we sum 1 plus 1 plus 0, that would be 2. That's even. 2 plus 0 is 2. Again, even. 2 plus 1, 4. Again, even. And so all of those would be anything that the sum of is equal to an even number, that would be expected. If it isn't, so if we look at, again, the 1, 0, 0, 1 plus 0 is 1, and that's odd, so it doesn't meet that rule, and so we wouldn't expect to see that 1, 0, 0, right? So this just, all these reflection rules of what's present talks about, then what is missing. So in BCC and FCC, there are different types of missing peaks based on the presence of that body-centered atom, or those face-centered atoms can actually cause missing or extinct peaks to occur.